Welcome back. So we're switching track a little bit, but hopefully you'll see a lot of connections between these two talks, and as Steve said, hopefully that's going to inspire some ideas following from this as well. So my name's Justin Sheffield. I'm head of school for Geography and Environmental Science, and it's my great pleasure to welcome you all to the second half of this inaugural lecture series, and to celebrate the promotion of our colleague, Professor Jules Leyland. So some of you know that Jules is a true product of the University of Southampton and our school. From his PhD way back in 2000, well actually not that far back, 2009, to professor most recently. He completed his PhD in coastal geomorphology, modeling long-term coastal gully evolution, and this laid the foundation for a career that's been focused on dynamic processes of coasts and fluvial systems. So way back, he started after his PhD as a geocomputational specialist. Do you remember that? Then lecturer in 2013, associate professor in 2018. So a steady but rapid trajectory, culminating in his well-deserved promotion to professor of physical geography towards the end of 2023. So it's gratifying to actually know that someone can have a very successful career and get to professorial status in a single institution. And, thinking about many of us here who've had to move around to actually develop our careers. So it's really good to see that and the support that you've been given over the years to do that. So today, Jules is internationally recognized as a geomorphologist specializing in sediment dynamics across various scales, from the smallest grain of sand to global systems, and from mountains all the way down to coastal regions. And a key aspect of his research is, and you'll see the connections with the previous talk, is the innovative approaches to environmental sensing using particularly high-resolution mobile surveying techniques, and applying these to understand the dynamics of the sometimes very small but right up to very large and complex systems like mega rivers and deltas. So these techniques span from uncrewed aerial vehicles, UAVs, terrestrial laser scanners, to advanced Earth observation techniques, and I'm sure we'll see lots of examples of that in his lecture. So I want to highlight something related to this, which is how this technology has enabled his founding and leadership of ESAS, which is the Environmental Sensing at Southampton Enterprise Group. So this is a rapidly developing activity in the school that also supports research and teaching, particularly aimed around the terrestrial marine interface that is there to really inform management decisions and interventions. And I've been really impressed about how Jules has developed this alongside the technical team to what is becoming a bit of a flagship activity for the school. So this has been really impressive. And Jules' research has yielded lots of tangible global impact, especially the significant work in Southeast Asia, looking at the environmental societal costs of sand mining, and this has received a lot of international media interest, so including input into documentaries for the BBC, for Vice News and South China Morning Post, and I'm sure we'll hear lots more about this in the talk. Likewise, the work that he and his team has led has directly shaped policy, resulting in the delivery of the first sand management plan for Vietnam, which is fantastic. So his research demonstrates that much sought bridging of fundamental science with pioneering technology and critical real-world policy application. So beyond his academic contributions, I've also been very grateful as head of school and the school in general for his exceptional leadership and collegiality within the school, particularly as the school's director of resources and infrastructure. And in this role, he has facilitated the development of a fantastic technical team and enabled vital investments in equipment and infrastructure, including refurbishment of much of the teaching and research labs, and that's an ongoing process. And most impressively in this role, he has taken on, I think, what is one of the hardest nuts to crack in academia, and that's to get academics to share their offices. Lots of work to be done. So above all, Jules is a genuinely engaged colleague, always interested in how to do science better, supporting, collaborating with, and learning from those around him. So join me in welcoming Professor Jules Leyland.
That was very kind. Thank you. thanks so much, Justin. That was a really very kind introduction. I'm going to just start my watch going so that I can keep a track of time. What an absolute pleasure to be here for this inaugural. Thanks for everybody for making the effort to come along. It's been really a pleasure and quite humbling to reflect upon the work that shaped my career. And I want to tell a story tonight. Move forward. I'm going to have to, use the clicker. So I want to tell a story about a particle, about a piece of sediment. So this particle, very small but mighty, sits up on the source zone of our AI-generated river system over here, ChatGPT special. Sits on the hillside here, this pebble. But it's going to move down through our system, through this transfer zone. It's going to be bashed around and abraded and knocked around so it gets finer into bits of sand and ultimately end up in the sink zone of the fluvial system at the ocean, in some of the world's great deltas and out into the offshore as well. So I'm going to tell a story from source to sink. This is a concept that we're going to use to frame some of the research that I've been involved with over the years. And alongside that, we're going to also talk about a range of different scales. And this has been, as Justin pointed out, a kind of feature of my research is that I've worked from very fine scales using very cool techniques like laser scanning, right up to global scale, kind of use these fine scales to inform our understanding of the global scale using things like Earth observation, so satellite sensing with drones and autonomous boats and stuff. So some of the things that are quite similar to those that Steph uses as well. So before we start our kind of sediment journey, I'm going to take a few moments to, if you'll indulge me, to talk about my own foundations and the kind of source zone of my career and my beginnings. So here's a young me, but really delighted that my mum and dad, Viv and Ty, are here. I think my sister is joining online as well. We had lots of amazing holidays up to Lake District when I was young, places like Norfolk and the lakes, and this looks idyllic, but I was actually cooling blisters from the ill-fitting wellies here. And yeah, lots of, again, asked Mum to send me some pickies, and these were what came back. So me and my sister sat in rivers, but a real affinity for the outdoors, and got involved in scouts and cadets and that sort of thing, and often milling around in the outdoors. And I think this has definitely sparked a passion for the outdoors and things like pond dipping and stuff. This is a great one. Very happy family, great. Thanks, Mum and Dad, for everything. But this image as well, for any mates that might eventually watch this lecture, I joined Queen Mary's Grammar School a little later. We moved to the area, and in year 8, I joined this great school in Walsall. And my friends remember this slightly cheeky guy coming with curtains, this step haircut, and cotton wool in my ear. And those of you that know me now, I'm still deaf in one ear. And there I am with my cotton wool. I think this must have been just about the time I joined Queen Mary's Grammar School. So those people can go into they can be particles in our river system. I also owe a huge debt of gratitude to this chap, and hopefully he's been able to join online. This is Steve Law, my geography teacher from school. Steve was head of geography at QM. But when I was thinking back on this, great teacher, really did spark a passion for physical geography in me. But actually, the stuff that was really formative, the things I remember most about Queen Mary's Grammar School was this amazing place they had. They'd been bequeathed this little coach house in a place called Farkinnis on the Barmouth Estuary. So about 100 miles from school, on Friday afternoons, some of these teachers, it's quite exceptional looking back, right? They used to finish a week at school with all these horrible, snotty little kids, and then they'd pile some of them into a minibus and spend their weekend at Farkinnis with us, doing all sorts of amazing things. And on the route, you could look at exciting things like the dead end on the M54. This is something they handed out to look at, and more exciting things like Snowdonia National Park sign. This was the coach house. It's a tiny little place, had this classroom attached, but it was magical. Going there was just like completely different, and we were afforded so much kind of autonomy there, and off we went into the countryside, often unaccompanied. I remember about 12 years old doing the Farkiness Run. It was about a half marathon, and they just let us loose on the roads and said, there's a map, and off we went. And a few made it back, most got picked up later in the dark in a minibus. But it was fantastic. And but coming back to the geography, this sat in the in the shadow of Cadair Idris, this place, and you can see there Cwm Cow and this beautiful landform and geography field trip that was held here with Steve Law was honestly really formative in my decision to then carry on in geography. So huge thanks to Steve and to QM as well. Off I went to Southampton Uni and met this quite shy and retiring young lady. She used to squirrel herself away in halls, but we hit it off and eventually ended up getting married in 2009. And I'm also really pleased that Daniel and Oliver are here as well tonight. So I'm very fortunate to have a really supportive family who also like playing in rivers. And we even have lunch on rivers. This is in Croatia last year. And honestly, I wouldn't wish to spend that time when I'm not working with anybody else. And Rach works incredibly hard herself, and I know it's really hard supporting somebody that's off for 2 or 3 weeks doing field work in Cambodia or wherever it might be. So thank you, all of you. Also means I've inherited another bunch of families. So Phil and Liz are here as well. My amazing brother-in-law and sister-in-law who I think are online, Matt and Ellen, and Pam and Mike as well, who are like other parents-in-law to us. And my sister's boys as well, Harry and Sammy. So I'm just incredibly well supported. And it's going to be a feature of my talk tonight, really thanking other people and that have supported me. It's such a team game getting here. And as Steph noticed, we work with so many other people as well. So huge thanks to them. So back to sorry, Steve. Back to the University of Southampton, and Justin said, I am quite unusual. Steve turned around and whispered, unless you're at Oxford, because if you're at Oxford, you can stay there all the time, and it's fine, right? And it's absolutely right. But it's quite unusual, actually, to have somebody that has managed to stick it out and had the opportunity to stick it out at a single institution. And it's in no small part due to Steve. I owe Steve another huge debt of gratitude. So came here 2001 and didn't stumble across Steve until 2003 when he led the Arolla field course, which those of us in geography will be well aware of. So it's another deeply immersive field course that we teach. And once again, at university, that was the point that it all started clicking. It was the first time I actually saw things in rivers moving, right? So, and again, that was just, it's sort of eye-opening when you actually see stuff happening like that. A PhD, Steve advertised a PhD. I had no intention of doing a PhD at the time. It hadn't really crossed my mind. And I saw this thing, I was like, wow, that just sounds and looks amazing. Actually, that's something you can actually do. And the rest is kind of history, but that opportunity was afforded, and I was fortunate enough to end up doing that PhD. And another group of great friends and mentors and colleagues who I've been really lucky to have in the department. Paul has also joined us tonight. Paul's now retired, but in my early career especially, and still working now, doing more research, I think, since you've retired, Paul, than you did when you were in the department, but has been an incredible friend and mentor to me. Joe's one of the most generous people, academically and personally, that I know. And Pete and Eli have been really great friends in the department and mentors too. And as is Jim Best, who's Illinois, but somebody that has offered very sage advice through my career. So I want to say a huge thank you to all of them too. All right, so on with the show, and let's get back to our particle. So this particle begins its journey on one of these hill slopes. Sat there, might be mobilised under gravitational processes. It falls down into our river system. And this is actually in Arolla. This is a photo I took this year when I led the field trip. There's some students in a river. You can see all these huge particles sat in the river. And at some point, they're mobilised. The river will pick them up and move them downstream. All right, so simple, deceptively simple question that underpinned some of the early research we did was, well, how do these gravel particles move, and why are our models so rubbish, right? That's not the name of the paper, by the way. I'm paraphrasing slightly here. But to explain this, a little bit of simple sort of gravel mechanics. The models that we had basically assume circles or spheres, right? So you've got all your particles arranged next to each other. You apply some force from the water, the river water, and the model is basically a simple moment, a pivoting model of how a particle might move over a single pivot point on another one, right? So, okay, seems reasonable that if you've got an arrangement of particles, that's what might happen. But of course, you only need to look at the picture here and this flume that we set up to see that particles aren't spherical and they're not round, so that's not really very realistic. So what we really set out to do is actually measure the realistic 3D shape of the particles. We made use of this fantastic resource at Southampton called MUVIS. It's an XCT scanner, so an X-ray computed tomography scanner, a bit like the ones you have in a hospital, very high powered. We basically built this prototype scale river channel based on one in the UK. We then, at the end of running water through this flume, so we water work the sediment, we'd then pour wax onto parts of the sediment that were buried in baskets so that we stabilised it, very carefully excavated it, and here they are inside the CT scanner. So it enables us to build out, use this, to build these beautiful 3D models. So here's an exploded view of one of these baskets. And you can see the complexity of the arrangements of the grains, but also the shape of them and the fact that if you put all those together, they haven't just got one contact point. They might have 2, 3, 4, 5 contact points with other particles. And all credit here to our postdoc on this project. I should say this was research that was led by Rebecca Hodge at Durham. David Sear was really instrumental. Some of his early work underpinned our theories that we were testing here. But Howe developed this new 3D vector mechanics model. So basically, it was taking all those complex 3D interactions of the grains and creating a 3D representation of how grains move. What that allowed us to do basically is kind of recalibrate those simple models that we had from spheres and say, okay, we can now account for a bit more of the uncertainty there. Turns out those exposure areas, so this is basically the part of the, if you think this is sat on a riverbed, flow is coming across the screen left to right and hitting this part of the pebble that's exposed. That's still a really important metric in how gravels move. And work's ongoing here. I know Rebecca's she's recently won a new grant to look at then how the sort of cementing effect of very fine particles in clays around these pebbles also impact sediment transport. So, okay, we understand something about how our particle moves. It's beginning to move downstream. That takes us into a different part of our sort of hypothetical system, into this transfer zone, or the sediment remobilisation zone. This is the part of the river network where channels are depositing sediment, remobilising sediment, meandering, moving around, so really dynamic. Lots of fine sediment by this point, so things are broken down. We've got sand in there. And work here really crosses a couple of continents. So I'll start with an example from Italy, some work that Steve and Massimo Rinaldi are involved with, and then talk about some of the work that we did in the Mekong as well, where we're going to spend a bit of time today. But the question here that emerges was around why do banks sometimes erode under, let's say, high flow conditions, but then stop? Right, so under the same high flow conditions, they erode, but then there's periods of relative quiescence where it slows down. So what's going on with this bank erosion? Okay, so to understand this, or the way that we set this up, a little bit of theory about how banks erode. What we're looking at on this top image is it's a plan view looking down on a riverbank. So this is our flow, and these bumps represent the bumpiness of a riverbank as we're looking down on it. And basically, the way that we think about riverbank erosion is through the amount of shear stress that's exerted on a riverbank. Okay, so stress, essentially, the force of the flow hitting a riverbank. And that shear stress can be broken down into two components that are relevant here, and that's the form drag, right? That's literally the form roughness. So the amount of shear stress that's attributed to these form elements here, and the skin friction component of that. So the skin friction component is the very small stuff, right? So it's the micro variability or topography of these banks. And the way to think about bank erosion is that it's a kind of a ratio, if you like, a trade-off between the form drag component, because the form actually has the effect of shearing flow off, and in this boundary layer region, exerting less force on the riverbank. So it actually protects the riverbank downflow of the bump elements. And it's the relative proportion of the skin friction component, right, compared to the form drag, that means if there's more of that then there's more hydraulic erosion. So higher form drag, lower skin friction, you get less erosion, more skin friction, and lower form drag, you get more hydraulic erosion. And we were using this, we were using this very simple analytical representation that was proposed by a couple of guys called Keane and Smith in the US. And what they basically did is they approximated the form roughness components as Gaussian bumps. And that's just a way of simplifying the bumps of the riverbank so that we can get some regular metrics of, sorry, keep pressing that, the height, the downstream length of these things, and the spacing, lambda, between them. Long and the short of it is, to do this, these guys had to get very high resolution measurements of a bank, and they did this manually. They got a meter ruler, and they measured points to the bank to try and build out some high resolution topography of the riverbank. So what we did to kind of move this forward is took advantage of some of these really cool survey techniques, in this case terrestrial laser scanning. So the department invested in one of these scanners way back in 2009, 2010, and Joe and I are somebody that have both used the laser scanners a lot in lots of well, certainly with the earlier research that I've done, and now with some of the mobile stuff, and Joe's very much still using it as well. What we're able to do, this is our riverbank, this is the bank in Italy. It's about 4 meters high. This is a relatively short section of riverbank. It's about 60 meters long. You can see that it's in the summer here. It's an ephemeral river, so we're very fortunate. We don't get much flow in the summer through this river, so we've got a full bank exposed, and we can take these beautiful scans of the riverbank. And from those, we can extract all sorts of cool metrics, because we are scanning at millimeter resolution these riverbanks, so we're actually detecting the skin friction and the form drag components of the shear stress here. And we're doing this, multiple times over the course of 5 or 6 years. So what we're looking at there is dark colours are further away from us and the light colours are closer. It's basically just giving us a map, very high resolution map of the riverbank. We can also then look at the amount of erosion, the amount of material that's been eroded in between each of those surveys. So dark colours, lots of erosion. These lighter colours, less erosion. And what you see is, of course, that there are patterns. So things erode in certain shapes. So this is a good example of where you'd be increasing the form drag through little pockets of erosion happening that are making bumps on the riverbank. So if we put all this together, and this is how we end up at some of the sort of conclusions that we drew with this work, you end up with, so here's the flow discharge, these bars along the bottom here. So you've got some very high flow discharge, much lower stuff here. You've got the total amount of erosion that's occurring, and each of our surveys layered on as lines on this time series. And importantly, the coloured lines then, remember I said about this balance between the drag and the skin friction component. The blue line is drag component, and the red line is the skin friction component. And what we're basically seeing is that if you get an erosion event, you get an instantaneous increase in the form drag, so bumpy riverbank, that then basically has the effect of protecting that riverbank. So although you might get other high flow events, those slumped blocks and the high drag shear that you get there basically has a protective effect. But then over the course of maybe a season or more, as you get other flows, maybe other subaerial processes, this is trimmed back, it's smoothed. And ultimately, it's that smoothing and the reduction in the form drag component which means that primes the riverbank again for increased erosion. So you get this sort of feedback or cyclical nature or self-limiting erosion mechanism. So we've We know a little bit then about these, how banks evolve, and then we can start looking at bigger rivers. Okay, so here you go. Here's this is a shot of the Mekong River. 2013, this is a project that Steve led. I was a co-investigator on. My component on this was to start thinking about basically taking that work that we'd done somewhere like Italy and the Chechnya and applying it to these sorts of locations. It's a whole different scale. So I said we'd cross scales, and some of you in the room that I'll come to later are working out here at the moment as well with me. These riverbanks are monstrous. You can see huge. I still struggle with, is this a form roughness or is it a landform roughness? To quantify this is quite tricky, but we've got maybe 10 metres of riverbank above the waterline. There could be another 20, 25 metres below the waterline here. So measuring these things in the same way is really tricky. We've got rivers that are up to 1 kilometre or more wide. So I'll come on to how we did it in a moment. But a bit of context. What we were trying to do on this project was not just look at the riverbanks, but look at all components of the sediment load. So the idea was to really resolve the sediment budget in a transfer zone. That was kind of Steve's master plan when putting the bid together. We also wanted to kind of look at some of the drivers, and we really by chance happened to have an opportunity to do that with a very extreme event that happened, and that's this tropical cyclone Wu-tip. So these are cyclone tracks layered on. I'm not going to go into the detail of this. This was some work that Steve led looking at the impact of cyclones on hydroclimatology and sediment delivery. But you can see the red is basically the precipitation that we attribute to those cyclones. This was a huge cyclone that tracked across the basin just as we were in the field measuring data. This is the flow hydrograph here of the Mekong over a course of a couple of years. And that red dotted line is this thing tracking over, dumping loads of water. And you can see, here's the hydrograph, there's the annual average hydrograph, and there's this huge peak that's attributable to Wu-tip. So we were out measuring data on this, and it gave us quite a unique opportunity to see how an extreme event actually impacts something like bank erosion and sediment delivery for a reach. So back to the cool tech that we use. This is a setup that we had in the field. Wrong button again. We've got a mobile laser scanning setup here. So one of at the ground-based LiDARs, but basically configured to do mobile work with a motion sensor and a multi-beam echo sounder to measure below the water. We also have an ADCP. This is an acoustic Doppler current profiler. So it's an instrument that can measure the velocity of the water in transects across the water. But it does it using the Doppler shift. And it measures the Doppler shift off particles in the water, which is really helpful for us because we can actually calibrate the backscatter of that instrument and also get really good estimates of the amount of suspended sediment in the water too. So we can build out these models that look a little bit like the type of thing we developed on the Chechnya River in Italy. So this is actually the volumetric erosion between some different surveys here. But you can see, so again, yellow is less erosion, red is high erosion that we can attribute to Wu-tip, for example, for that extreme hydroclimatology, and that we get these big sort of embayments forming as well, so that we can start looking at the actual shapes and mechanisms of erosion too. And alongside the backscatter, or the calibrated backscatter from the ADCP, which gives us these suspended sediment estimates here as well. So again, we were able to look at the patterns of suspended sediment in the flow for different regions of the river, but also between the different time periods. And ultimately put all this together to build out a bit of a budget through this reach with the influence of this hurricane. And the upshot of this, the upshot actually in this reach with this very rapidly eroding riverbank, one of the take-homes was that about 10% of the sediment load fluxing through this reach was attributable to direct bank erosion, which is really quite stunning actually, because there's a lot of sediment, as I said, fluxing through this reach. Okay, so this point on our journey then, that sediment particle has experienced entrainment, it's been deposited, it's been eroded again, it's perhaps been moving downstream, whatever. But wait, we're missing something here. There's a big part of the complexity of this story that I've completely ignored, and that's something that's sort of nagged away at me for years and continues to do so. And people in this room will know why. So this is back to the Chechen River, and that's me. I haven't fallen off. I'm trying to remove bits of vegetation on the bank. And I always found that when I look back on this, I still find it weird. And it's because we had the laser scanner, and I was desperate to try and characterise the skin friction, the bumps and everything. We wanted the veg gone, so I was trying to sort of carefully remove it. But of course, it's sort of cheating doing that, isn't it? Because this is a really important part of the roughness signal. And back to the Mekong. Veg is there, it exists. We can't really ignore it, but it's really complicated. So again, some more people, and there are others here, but it's something I keep returning to. Greg Vassilopoulos, who's a lecturer up at Hull Uni now, Joe and I supervised a PhD. I'll show you a bit of the work that we did with Greg. Chris has tackled this in his PhD work as well. Dan continues to tackle it at the moment. And Paul and I have ventured into this with flow across vegetated floodplains as well. So the question that we want to sort of think about is, okay, let's think about veg. How does that impact sediment and the mobilisation processes? Right, so again, back to the core techniques, and that's really what underpins a lot of this. So this is why Joe and I ended up together doing this. Joe works with fluid flows too, but with air. And we're like, okay, well, we've got the capability now to quantify these sorts of things, right? Complex vegetation. So what Greg did is actually bought a bunch of fake plants, right? This is a little fig tree about this big, and grasses and other things, and laser scanned them and built these really high resolution 3D voxel-based models. They're essentially porosity models. So able to quantify the vegetation accurately. He could then drop it into a little recirculating flume, carefully control the flow that was going through the flume, measure the flow fields using ADVs, acoustic Doppler velocimeters, and build these beautiful visualizations of how vegetation impacts the flow, and actually using through water laser scanning how the vegetation reconfigures itself under flow conditions as well. That's as far as Greg took it. It's amazing work. Didn't get to the point of of sediment impacts. Chris really extended this. It's about scaling up and taking this out into the real world. So Chris actually basically took this and packaged it into something tiny with a motion sensor and put it on a drone. So there's some technical development here. And then started to think a bit differently about vegetation as well, by thinking about functional grouping of vegetation and traits. So again, a slightly different and quite novel approach to doing this. And also looking at things like seasonality. So you can see some things like grasses, there's not such a strong seasonal picture, but through single-stemmed and branching things, stuff that has leaves and die back, there's quite a strong seasonal signal. And Chris, basically with his techniques that he developed, was then able to cover large areas, so about a kilometre or kilometre and a half of the River Team here, and looking at interactions between all sorts of different veg along here and the geomorphology of the river channel. Including trees and the stabilizing effect that they have, but also grasses on floodplains and the roughness that they exert on flood celerity waves. One thing I'll note here that's really difficult though is you get the tree canopy in these sort of forested areas, but nothing below them. And that's actually work that Dan's doing now in the understory. So we're starting to tackle what happens beneath the trees. It's a really challenging area to work, and Dan's making use of things like backpack laser scanning and ground-based terrestrial laser scanning too in those areas. So I suppose the message from this, and it's an ongoing one, is that we've really got to think about vegetation as part of that geomorphic signature. It's very much part of it's very much influencing what happens with the geomorphology. All right, so our grain has moved, it's been entrained, it's been dumped out, it's been remobilized, it's been caught up in, snared up in vegetation. So we now move down to the Mekong Delta. So this is critically important sink zone within the global sediment cascade, supporting more than 20 million people, and it's fundamentally shaped by the delivery of sediment and mud. But it's under extreme pressure, so incredibly vulnerable landscape. One of those pressures is from dams, of course. So what we've got here, a bunch of already built dams up in China. There's planned and under construction dams through Laos and some in Cambodia too. So clearly they're going to have an impact on sediment. They're going to hold sediment up and stop it reaching the delta. But also they're under pressure from sand mining. So this is a picture, an image, a drone image of the Cambodian-Vietnamese border. And you can see all of these sand vessels, some are fully laden, some are empty, that are basically ready to cross the border, take sand that's been extracted in Cambodia and deliver it to Vietnam. It's extracted in Cambodia using suction barges, so suction dredging, or huge bucket dredgers down in Vietnam as well. And lots of it ends up here, back out on the land. So we're just shifting it from one place to another in our sediment system, anthropogenically. So this is basically used for levelling, infilling these huge wetland expanses with maybe 4 or 5 metres of levelling sand. And of course, once you've levelled it out, then they'll want to build on it. So that the same sharp sand that we get from the rivers and the coasts is used in concrete production too. And I should add, it's sharp sand, not the rounded desert sand. So Joe's desert sand is no good to us here. It's no good for concrete production because it's too rounded. So it doesn't bind with the cement to make good concrete. So research that I led a GCRF project that we had looking at the impacts of sand mining on rivers and its banks, and importantly, how much is being extracted. So what's happening to the river banks here and how much sand's being taken. So Shad Magdalena and Chris Hackney at Newcastle are instrumental in delivering some of this research with us, along with a big team of people, as ever, that I worked with. So here's a bit of beautiful multi-beam data from the Mekong, and this was actually collected in our earlier research trips, so this will be sometime, I think, from 2013 or 14. But what you're seeing, there's your natural riverbed with beautiful dune features, and then here, this is where the sand extraction, so suction dredging, has taken place. It's on a huge scale. I said the Mekong's massive. Some of these are 8-10 metres deep, 40 metres wide, 70 metres, so with massive amounts of sediment being extracted. And if I give you a very, very brief riverbank 101 here, if you've got your pre-mining riverbank that's in some kind of dynamic, stable equilibrium, then you suck out a load of sediment off that riverbed, so therefore deepening the bank or extending a bank and over-steepening this toe, that's what can trigger bank failure and bank erosion. So basically, this was work that Chris led up in Cambodia originally, we were linking this sand extraction directly to the bank erosion processes. And indeed, that's what we see throughout the delta. This is in Vietnam, but in Cambodia too. Loss of homes and infrastructure driven by bank erosion, some of which can be attributed to sand mining activities. So the way we studied this, this was work that Andrea, who's also here today, the modelling that Andrea led using a finite seepage model, geoslope. We can set a model up to basically simulate the bank erosion processes and then run this model many times, turning the dial on things like what happens if we have a steeper bank, what happens if we have different bank heights, and indeed what happens if we have more or less flow through the river as well. So build out a whole bunch of different model results to give us these stability charts. And basically, this is for a single site. We've got a bunch of bank heights here, different bank angles along the x-axis, and this is the FOS is factor of safety. So a higher factor of safety means it's more stable, and anything over 1 would be, under 1 would be unstable on these banks. With something that's potentially either or, depending on the flow conditions in between, what we'd call seasonally unstable or dynamically unstable in between. And we can build these sort of these cartoon models, if you will, for each of our sites of bank stability. So I'll come back to those in a moment, but that's how the banks respond. The other thing we wanted to know is how much activity is taking place, so how much sand's being extracted. Really not an easy question to answer because it's massively unregulated in Cambodia and Vietnam. So there are licenses for sand extraction, and they're given out. There's a lot of corruption occurring here, so lots of money changing hands, but an awful lot of illegal sand mining takes place too. So work that Magda and Chris led, as I said, as part of our GCRF project, looked to use very high-resolution PlanetScope data. So these are daily satellite images to build up something we've termed the human waterway footprint. The human waterway, we called it the human waterway footprint because we couldn't really be sure that it was all sand barges. So what we're detecting here is vessels and extraction pumps and other things on there. It's a good proxy for the sand barges, and we did have people on the ground in country saying, yeah, we've done counts and we can sort of match those to them, but there are limitations to this approach. But we get these nice heat maps. The hot colours are more vessels per kilometre squared, and the dark colours less vessels, and they correspond to the areas where we are seeing, for example, more bank erosion. Chris led some work using the same sort of high-resolution data to look at the amount of bank erosion that was taking place. So you can put those two things together, and I want to focus on this area in the delta here, to build out these really pretty risk maps. So again, credit to Chris Toms, who sat over there, who put all of this complex data together for us. But I'll try and talk through one of these. You've got these little different inset panels that correspond to the panels here. Let's talk about this one up here. The dark red colour is an output from our bank erosion model. And the dark red means basically that bank is already unstable. So it's stuffed, it's already collapsing at the moment. If we've got green banks, then the different colours here, from light green to dark green, basically show the amount of tolerance that bank has before it will become unstable under different sand mining scenarios. So dark green means you might be able to have up to 5 metres of bed level lowering before it triggers a shift into the unstable regime. Also on these plots, we've got sand stock depth. So this was a really cool data set that was collected by our colleagues at Deltares as part of, this was subsequent work with WWF here that we were putting together. And basically what we're able to do is using these maps is say, okay, we've got banks that are unstable, we've got the amount of sand that may be or maybe isn't available. Can we target where sand extraction might take place? And we can go a step further. So Duncan sat here. Duncan built beautiful land cover land use maps for us as part of this, new really high resolution maps for the delta. And we've got land value from our partners at Canto University as well. So we can layer that information onto these maps and say, well, actually, if you target this area, there's a bit of sand up there for you to actually dredge. And maybe if you focus it over this side of the river, that there's a bit more tolerance of that bank in terms of triggering erosion. And of course, it might be that that's an area that hasn't got as much infrastructure or population. So these maps are actually have been used as part of the sand management plan work that Steve and I have been delivering with colleagues in Cambodia as part of that WWF project. And now they're starting to filter through into decisions that are being made in the Delta, which is kind of really satisfying to see science impacting policy. So, all right, our grain has now been taken out of the river. It's been chucked somewhere else. It's been levelled. It's been put into concrete. It's found its way to the delta, maybe. I just want to, if you will, take a step back and say, well, okay, is that happening everywhere? Is the Mekong typical, or are other river systems globally behaving in a different way? And this is a current project, so a project that we're actively engaged in at the moment, and Tom and Steve and Howways, postdoc, and Chris has been involved as well previously, and others as well, as part of GLOS, Global Suspended Sediment. And the premise behind GLOS is really pretty simple, actually. You just got to look at these two images. Same satellite image taken, this is Yangtze River, pre-dam and post-dam. And what I'm looking at here is really simple. It's the colour of the water. It turns out satellites are really good at picking up the colour of the water. And we're fortunate enough to have this fantastic data set called Landsat. Many of you will use that covers about 40 years, so more or less weekly images. Now they're weekly, over about a 40-year period. So a very rich data set that we can leverage. So this is all credit to Howway from recent, and this is really hot off the press, this stuff. It's stuff that we're actively doing at the moment. How are we building out these global maps of sediment flux? So we take, again, Steph talked about this earlier, very sparse data sets. And they really are incredibly sparse. You can see we're missing vast swathes of the planet here, but we've got some good data in China and Southeast Asia, North and South America, a bit in Europe. And these are observations of sediment and discharge, so flux of sediment through river systems. We need a typology to build our model onto as well. And as a very brief aside, it's quite fascinating actually that we didn't really have very good maps of rivers until recently. And so I find this quite mind-blowing. If you think about maps of our roads in the UK, for example, we've had superb maps of those from Ordnance Survey for years. But global river maps are derived differently. Traditionally, they've been derived from digital elevation models from things like the shuttle radar mission, right? So coarse maps of models of the Earth's surface where we route water down them, and then we look at where the water flows and we build out very simple, quite coarse maps that look something like this hydrosheds model here. And as part of another project, I haven't got time to go into it today, but it's been really fascinating working and led out of Oxford with Louise and Mikhail. We've recently published this GRIT, Global River Topology data set, which is a bit of a revolution, actually, in river topology that includes complex bifurcating, so splitting and joining river channels at unprecedented scale. So we're fortunate that we could make use of this in our project, and that's the topology that Howway's been using. We take our Landsat data catalogue, we then combine it with some measure of river slope and discharge because we're interested, if you recall, in the flux, not just the amount of sediment in the river, but how much is moving through the river. And that gives us, ultimately, these maps of global sediment flux. And this is the sort of thing we get. So this, as I said, is really hot off the press, and how we're still working on this at the moment. This is just the mean average suspended sediment flux. So it's basically the mean over 40 years of Landsat data. So in some ways, it's saying something, but not a lot. We've got such a rich data set. What we've actually got is monthly flux from our data set over 40 years. But there's some cool pictures in here. You can see big rivers that we might expect to be fluxing lots of sediment on average from the Mississippi and the Amazon, Yangtze, Mekong coming through here as well. And you can also see, you know, the patterns in terms of northern, southern hemispheres. What we're starting to do with that now is look at the trends. So it gets more interesting when you look at how things are changing through time. So again, this is simple in that it's just taking the 40-year trend, so the mean trend of the mean change over 40 years. But some interesting patterns already start emerging. And one of the real novelties in what we're doing with this is that we're not just looking at flux at the ocean, we're looking at sediment flux through the whole river reach. So every segment, they're about 1 kilometre river segments. So we're starting now to look at signals of when things changed, how much they changed by, And we're also, really excitingly, starting to explore what's driving those. So we're taking a whole bunch of other data sets, things like soil moisture and land cover and precipitation and temperature, and throwing those into this Bayesian network model and starting to explore then what is driving the changing trends of sediment. So some exciting results to come, and Harry's going to be presenting some of this at AGU. Right, I'm just getting there now, so wrapping up. So I did promise some societies in this as well, that said our particle, which is now part of a global picture, it's travelled down from our source zone, down into the delta, we've zoomed out at a global level. But that particle, at a global level and thinking about satellite data isn't really telling us anything about communities and social and cultural and economic values. You've got to go back to people. So that's where I want to finish up today. And really cool, exciting project that I'm involved with at the moment. So I'm leading this project, Hidden Sand, with again, it's always big teams of people that make it a joy to do. And again, delighted I've seen Peter in the audience and Alexandra, who's joined us as well. Chris is working on this alongside a bunch of other people as well, including colleagues in Cambodia. So how do social and cultural and economic values link back to sand and perceptions of sand as a resource? So this is work that's ongoing. We've only quite recently started this. It's a really ambitious project. It was funded by the UKRI Cross-Council Scheme. So it's bringing together a whole bunch of different disciplines and thinking about things a bit differently. This is our key study site, Rockakong Commune, just north of Phnom Penh in Cambodia. And it's a site, as you can see, that's been heavily impacted by bank erosion. These are some efforts to fix the banks, if you like, woefully inadequate efforts, I'll add, not least because they're all happening at the top of the riverbank. And as I explained, you can't see it here, but there's a good 20 or 30 metres of riverbank below those sandbags. So they might have a short-term impact, but ultimately these banks are primed to erode again. We're working with the communities here. We're collecting loads of social and economic data. We've just had Cambodian colleagues complete a survey of over 4,000 individuals in 200 communities across the whole river system. Alexandra's working with artists in the community as well. I'll come to that in a little while. And what we're trying to do is, if you like, marry up the physical, the sort of operational and management, the cultural, the social, and everything, and sort of put it into a melding pot. And I'm really interested in this. This is the work that Gustavo's been leading. It goes back to the PlanetScope data, the vessel tracking stuff. What we're trying to do is extend that out into a bit more of an operational system for monitoring traffic. And we've installed a network of ground-based cameras. And using some cool image processing techniques, we're now able to automate the detection of vessels. So we've got images being snapped every 5 minutes as vessels move up and down the river. And we can build out these really cool data sets now. This is a few months in 2024, looking at the direction of transport, so upriver, downriver, and also whether vessels are static. And what we're able to do, of course, is with that data, so we've got literally high-resolution 5-minute data, is calibrate the satellite imagery from PlanetScope and even Sentinel, which is a radar data set which is not affected by cloud, so we can get much more accurate measures of how much sand is being extracted, where from, and where it's moving to as well. So this is, again, ongoing work, but we're hoping that we'll actually be able to deliver an operational tool for managing and monitoring vessel activity. And then to sort of finish up here, these are some images from previous exhibits, art installations and that have been delivered linked with sand. So the communities have been thinking about sand and the impacts of sand for a number of years, and delighted that Alexandra is part of our project and is going to be kind of extending this and working with artists and communities and actually sharing some of the work that we're doing in terms of the monitoring and the multi-beam echo sounding and that type of thing, so that we can bring it all back together to understand the cultural impacts of sand. Right, I'm about to wrap up now. So that particle has travelled a long way. We've been from the hill slope down through the river system, bars. We've been eroded. We've been grabbed out through suction dredgers. We've been used for concrete production. It's had quite an arduous journey. But I've kind of wanted to show that sediment it's not just a physical material, right? It's very much a dynamic part of landscape development, drivers of hazard, and indeed that it connects geomorphology and society and economics and ecology too. And really, it sort of reflects my own journey as well. I've said that it's been very much a journey that's been supported by other people, and I have wanted to celebrate those teams and all those people I've worked with. And I think this is most of the people that I've published with, if not all. I'm bound to have missed some, all those that have been supporting me. So I want to finish by saying a huge thank you to everybody, and that includes people like Peter and the technical team, some of whom are here tonight as well. But anyway, thank you very much.
Thank you, Jules. Thanks a lot. Really interesting. That's a lot of bobbly heads up there, isn't it? So we have time for questions. So who wants to ask the first question? You're all itching to ask a question, I know. Here's one, John. Wait for the...
So lots of things to think about. I just actually, particularly with the sand stock depth, but also thinking about your global flux project, made me wonder about how long it takes to get particles down river systems and timescales with erosion. I wondered if you had any thoughts on that.
Yeah, wow, that's a really hard question to answer. Well, I mean, in some ways, John, it's precisely what we were trying to tackle in that early Mekong work, because I mean, as with lots of this, all the detail is lost, and I've kept it very high level. But what we were also doing there is coring floodplains. So we have got ages of deposits on floodplains. What I can tell you is that an awful lot of sediment makes it somewhere like the Mekong. So we've got these huge splay complexes. So these are offtakes as the river meanders down with these massive monsoonal river systems. You've got monstrous floodplains, and the water fluxes out over the banks through these splay complexes and deposits centimetres sometimes in a flood season of sediment. And the storage times there, might even need to look at Steve here for Rolf's storage times and those lead to 10 dates that they've got. I can't remember it off the top of my head, but it's a very dynamic system. The reality is that sediment's being stored on those floodplains, and certainly in the distal extents, for a long time. Whether our flux data set could ever be linked back to that in a more holistic way, I don't know, it'd be pretty complicated to do. But I'm not sure. It was a question more whether we can do it, or okay. It's something to think about, but it'd be incredibly tricky. I think we'd need a lot more data. So a lot of cores across floodplains to be able to map out those timescales of sequestration on that.
Other questions? Can't be getting that late, can it? I'll ask a question. So your kind of final map there, which was your initial assessment of kind of global fluxes of sediment and how they're changing.
The trends, yeah.
Yeah, so you said you were going to start to do some work, and you're doing it now to kind of figure out what is driving these trends. Yeah. So I imagine there's going to be some regional bits of dams that are influencing things. There could be some climate change impacts that's kind of affecting the flows. They're kind of changing as well. Is that what it will kind of look like, or would there be any places where there's just kind of natural processes that are driving change?
This is really interesting.
Is it all human-driven?
Very good question. I can't give you a definitive answer on this yet. So I'm looking a little bit at Howey, because he's working incredibly hard on this. And the Bayesian network model is the next stage of what we're doing. But we've got some early outputs that suggest that soil moisture, I've mentioned this, previously might be a really important driving factor here. So one of the things the Bayesian network model can do, this is why this is how Tom and Vera are involved in the model, so I blame them for the complexities of this beast. They've used these techniques a lot in previous work that they've done in deep geology. The Bayesian network model can look at the compounding impacts between different drivers, so the sort of much more complex signals that you get. So rather than just sticking a load of stuff into random forest machine learning, for example, and you get basically importance of different layers, we can say what happens if we take soil moisture alongside, and look at the impacts of that with precipitation. And that's something that we might expect actually is important for global sediment flux, because the soil moisture levels and the amount of precipitation that you get, so those sort of antecedent conditions, can actually impact the amount of sediment that's reaching the river channel. So, yeah.
We've got some questions online, but Steve's going to read them because I can't read them.
Okay, all right. You've not got your specs.
He left his glasses on the bench there. I can see them. So, Jules, this question is from Matthew Hartley. So thank you, Matthew, for the question. And it's much more straightforward than John's question, which is, what advice would you give to early career researchers aiming to make an impact in geomorphology today?
Oh, that's a good question. Thanks, Matthew. I suppose in some ways it depends how you define making an impact. We're all conditioned to think that impact is related to REF and impact case studies and this type of thing, which all of the academics in the room will be well aware of. But I think actually impact more broadly is about doing something that really interests you, and from which you can get some interesting answers. So, I mean, I often start with, when I'm talking with postgrads and other colleagues about, when they're starting out in research careers, saying, do something that you really enjoy. Make sure it's something that you're interested in, because if it isn't, it will be a hard slog. But I think the other thing that I've really benefited from, and I'm sort of unashamed to say it, is that you surround yourself with excellent people. This is a career that's been built on the back of colleagues, friends, mentors, PhD students. So I think in terms of developing a profile, work with other good groups and good people. And there's nothing wrong with that. You can hang on the coattails and off you go.
We've done it.
Yeah, absolutely.
Right. Anyone want to ask the last question here? Yes, Mike.
These are not, I'm so far out of my comfort zone with physical geography, but you focused quite a lot on a certain part of the world, and like adaptation is really context specific, depending on where you are globally and with the people. So will these results, would they be different if you did work like on the African continent in terms of what type of sediments there, what the flows of rivers are like, and what the communities are like, people?
Okay, so a good question. I mean, there's two, I suppose to unpack that, there's two components. So in terms of the physical science part of it, then I think the results that we're finding are probably broadly transferable, right? In terms of the physics of the system, how banks erode, how sediment and particles move through river systems. The part that absolutely isn't, and you're correct, is probably that latter part, the bit I just briefly touched on at the end, which is our hidden sand project. And clearly there it's incredibly community specific. So I haven't got experience of working in Africa, but colleagues in our department absolutely have. In fact, Justin works with people, especially around drought and stuff in Africa. But that local context is everything. So in terms of adaptation, I mean, in a simple, again, I haven't mentioned it, but the people we're working with here have already adapted in amazing ways to the river itself and the floods, right? They build their houses on stilts and stuff, and it's just, they're absolutely used to flooding. The bank erosion and the acceleration of bank erosion does feel like it's something different, right? And there's a real uproar in communities about that, and they are starting naturally to ask questions about the sand dredging and what's happening there. So I think the answer is yes, in other parts of the world, especially where we're dealing with the sort of social cultural aspects, it would be a very different context.
Okay, thanks, Jules. I think that's it. So can we thank Jules again for a fantastic talk and answers the questions?
Well, thanks, Jules. Thanks, Steph, again. Thanks all of you, both in the room and online, for your attention. Two absolutely fabulous talks, and I was delighted to see perhaps even more connections between them than I thought. Both of you dealing with really challenging problems at scale, large uncertainties, and trying to fuse the collection of new insights from new data collection efforts to inform our understanding and models of these systems. So the technological innovations, the approaches have a lot of common, and of course both really important implications for various societal problems as well. So in a moment, please do join me in thanking both of our speakers this evening, and then all of you in the room at least, with apologies to those of you online. We do have some snacks and some drinks to enjoy in the reception afterwards. But Steph, Jules, thank you both very much indeed.